the assignment, any issues that you're facing, or any of that sort? Okay, so if there are no issues, we can get started. So you should be able to see my screen now. So in the last class, what we were looking at is induction, right? So logic. We are looking at how all of the logical operators in Coq are actually built from more primitive constructions, in particular, just using inductive types and for all combinator, right? So those are the basic ingredients through which all of the combinators are described. And we also saw, I mean, the purpose of the lecture was twofold, right? The other purpose was to actually introduce you to tactics to deal with conjunction, disjunction, and other sort of constructions that you might encounter when you're proving real programs, right? So in this lecture, we are going to look at induction, right? So induction is one of the basic reasoning tools that we have, right, for logical reasoning. And you will see that induction is the most commonly used thing that we do in order to prove programs. So the reason why induction is so fundamental to doing things in Coq is basically the data that we describe in Coq, right, is an inductive type, which means it has some base case and a recursive case. And naturally, any proofs, any statements of truth that you want to express over such data will have to apply induction, right? So that's where that's why induction is so fundamental to proving things at Coq. And in this lecture, we'll introduce induction very slowly and then sort of see how we can do more complicated proofs. Okay, so we are going to prove some properties on lists that we had introduced in the functional programming lecture. So I'm importing all the list functions as well as list notations. And the first thing that I do is I do something very standard, right? This is a recursive function for append that takes two lists, list 1 and list 2. And then it is going to append, return a list which is obtained by appending list 1 to list 2. And we are describing it recursively. So we are pattern matching on list 1. If list 1 is empty, then you know that the append of list 1 and list 2 is going to be list 2. So if the list 1 is non-empty, then you take the tail of the list from list 1 and then append it to list 2, and then cons the head to the result list, right? So it's like peeling an onion. So you take one layer off, you recursively call append on the rest of the list, and then you say, okay, put that element back, and you will get the result. So we believe that this implementation implements append, right? And this is the same as what we had done in OCaml as well. And that's okay. So we have some expectations about the list, right? So let's prove some nice theorems on it. So the first theorem that we are going to say is nil lap, right? So if you take a nil list and then append it to any list at all, you'll get the same list, right? And this is sort of expected, right? So this is obvious because we know that is how it's going to work. Let's actually get Coq to agree that it is in fact the case, right? That is what we are going to do. So for all A, assuming that there is a list A, this property holds, right? Empty list appended to any list gives the same list. So let's prove this. So we do the introductions, and once you do the introductions, you are left with this term, right? Which is empty appended to list equals list. If you look at the definition of plus plus is basically append, right? I am just using the notation of append here. So plus plus is append in Coq. We use the @ symbol in OCaml. That's the only difference. So if you just look at the definition of append, right? If the left-hand side list is nil, then you are just going to return list 2, right? So simply applying the definition of append on this term should give you what you're looking for, which is just LST as a result. So the way we simply say by definition of the function, so the way we indicate that to Coq is using the simple tactic, right, which we had seen in the first lecture. Simple just says go and simplify every term that you can possibly simplify, right? And the only term that you can simplify in the goal is the goal on the left hand side. And if you simplify, you just get a list back. And equality is reflexive. This is trivially true, right? So trivially goes through. Okay, that's fine. But we also expect the the other way to also hold, right? So if you take any list at all and then append it to an empty list, you get the same list back, right? We expect this to be true, but it turns out that this proof is cannot go through by just using the tactics that we've learned so far, right? So we'll see how. So intuitively, we believe that this is true. So let's go ahead. So do the introductions, right? And then do the simplification. Can we try to do the simplification here, right? Earlier in the previous theorem, here when we simplified, right, we just got list. But we have a similar term here, right? The arguments are flipped. If I try to do simplification, nothing happens, right? And the reason nothing happens is simplification. Just look at the definition of the append function. And if you sort of follow the definition of append function says something about when list one is empty and list one is non-empty, right? But here list is an arbitrary list variable. We don't know anything about LST. So simplification just does not lead to any useful reductions. Okay, simplification is not possible, but we know list is constructed using nil and cons, right? So let us do case analysis on list. So the way you do case analysis is you destruct the list, right? So you get two cases, one for nil and one for cons. And for the nil case, it is simple. So for the first case, we need to show that empty list, cons to empty list, appended to empty list gives you an empty list. So trivial does simplification as well. So that one goes through. And for the second one, we have a non-empty list here, right? This is the second case. The case is non-empty, and we want to show that if you take a non-empty list and append it to an empty list, you get the same non-empty list. Now you can do simplification, right? And when you try to simplify, the definition of append is going to look at the second case here. It's going to pattern match with the second case, right? Oh, and it's going to say, I'm going to take the append of the tail and the list 2, and I'm going to append h to the front of it. So tail here is LST, this h is A, right? So all it's going to return is, when you simplify, it's going to say A, the head cons to, this head cons to, the result of appending tail with the list. So there is an implicit bracket here, right? The result of appending list to this empty list, and that is what you get, right? And at this point, we are basically stuck, right? Really, we wanted to prove this theorem, which is any list appended to an empty list gives you any list, which is where we are back at, right? So we are back at the same structure, the same shape of the structure that we wanted to prove, except that this is on the tail of the list, right? So that's the key observation here. So we wanted to prove something on a list. We are at a stage where we want to prove the same theorem on the tail of the list, right? But using the tactics we've seen so far, we cannot proceed. We are just stuck here because all we've learned is we can do simplification, we can do case analysis, we know how to split conjunction, disjunction, and so on, but we are stuck here, and we can't proceed at this point, right? Yeah, so we need to do something about using the fact that we are proving a certain property on a smaller sublist, right? We are going to use induction here, right? That's the next step. But Any questions on the things that we've introduced so far? Okay, so no questions. So it's clear now. So the thing to take away is observe that this term here, right, which is proving sort of equality of these two terms is the same as the one here. But even though we are using LST here, it's the sublist that we are proving this property on. Okay, we need to do an induction, right? So how does just to recall induction on lists, right? So how does induction on lists work? Suppose you have a theorem, right? That for all lists LST, you want to prove some property P on that list. This property could be arbitrary properties that you want to prove on the list. I'm just abstracting that to a P, right? You want to show that P of list holds. So how can you do induction on this list? So when you apply induction, you have to sort of do the base case and the inductive case. For the base case, you assume that list is empty, right? And you have to show that P of empty holds, right? P is the thing that you want to show holds on that list, right? P of empty holds. And for the inductive case, you assume that the list is non-empty with head H and tail T. This is the key bit, right? You assume the induction hypothesis, which says that this property which you want to prove, assume that it holds on the tail of the list, right? Because it's a smaller, structurally smaller, right? So it's constructed out of the tail. So assume that it holds on the tail of the list, and then show that this property actually holds on this entire list, which is head const to tail, right? This is induction on lists. And hence proved. If you can show both of these cases, you've proved that for all lists, LST, this property holds. And by applying induction, you get this induction hypothesis, which you don't get by just case analysis, right? If you just did case analysis, which is what we did earlier, you won't get this induction hypothesis, which you can apply. And here is how the same proof, how the proof could be written for the function that we are dealing with, right? So the property that we want to show is for all lists LST, list appended to an empty list is list. So let's apply induction on this list. The property P is actually this, right? This property that we are want to show. So if you apply induction, we want to first show the base case holds. So P of empty list holds, which if you just substitute the definition of P, we need to show that empty list plus empty list is empty list. And this is true, by simplification and reflexivity of equality. And then this is the interesting case, right? So for the inductive case, the list is going to be a non-empty one. You assume that P of T holds, right? It has a head H and a tail T. You assume that P of T holds, by which I mean that if you take the tail and append it to an empty list, you get the tail again, right? That's the induction hypothesis. Assuming this, we need to show P of H colon T holds, right? H const to T holds. So if you expand the definition of P, we want to show that if you take this H const T and append it to an empty list, that's the same as H const T. Do one step of simplification as we did earlier, right? So you get H const T, T plus empty list equals H const T. Now what you do is you apply the induction hypothesis, right? We know that T appended to an empty list is the same as T thanks to the induction hypothesis here. And you appeal to the induction hypothesis to rewrite the term to get H const T, which is the same as the RHS. And thanks to reflexivity of equality, this proof goes through, right? So one thing to remember is that in Cork, even though proof assistant is helping you, you are actually guiding the proof assistant in order to construct the proof, right? So if you don't have an intuitive understanding of what you're trying to prove and when you can apply the induction hypothesis and so on, you will be stuck, right? Cork is not going to magically say, oh, try this and try that. So it is, I at least for the first few examples, right, we will try to explicitly work through some of these things on paper. Like we are writing paper proofs here, right? And then once you get the intuition, you can proceed to the cock proof. Actually, when you get stuck with larger proofs, it is useful to actually come back and say, okay, do I really believe that this is true? Can I write a paper proof that I can convince myself that this is true? Then I will try to convince cock that this is true, right? So it is useful to do these sort of pen and paper reasoning even when you have proof assistance, right? Proof assistance can um, falsely lead you to believe that you can prove anything at all, right? Which is not at all true. So doing this sort of reasoning is useful. Let's actually, now that we've done the reasoning, we know this is how the proof is going to work. Let's actually go ahead and prove this in cock, right? So it's the same theorem as earlier. I think it's using nil instead of an empty list here, but it's the same thing, right? So so first do the introductions, right? We have an intros for A and list. Do those intros. Then we are going to apply a new tactic. So the last time we did unsuccessfully, we did case analysis on list, right? Now what we are going to do is to apply induction on the shape of the list. So this induction is actually driven by the definition of the list, right? The definition of the list has two constructors, one for nil and one for cons, and the induction is driven by the structure of the definition of the list data type, right? So when you apply induction on list, you get two cases, one for the base case and one for the inductive case. These two cases are made available exactly because your data type definition has two cases, right? So we have a new tactic here, just like destruct, we have a induction tactic. When you apply induction on a thing that can be inducted on, basically in cog, that just means an inductive type, right? That's the only thing that you can induct on. You get all the inductive cases that are possible for that particular induction. So the base case is simple again, right? We need to show empty list, appended to empty list is empty list. So simple and trivial makes it go through. And for the inductive case, observe that we have a new hypothesis, right? This is the induction hypothesis for the list, right? Which says that for the tail, which is the LST here, the list appended to the tail is going to be list. So we have this thanks to the induction hypothesis, and we want to show this term is true, right? So we do as before, we simplify. So when you simplify, all that has happened is this bracket has moved from here to here, thanks to the definition of append, right? At this point, you know that this term is the same as the term here. And if you replace this term with LST here, you will have the same LHS and RHS, right? We haven't seen a way to do this substitution, this sort of rewriting. And we are going to introduce this new tactic called rewrite. So rewrite takes a equality hypothesis assumption, right? So you can rewrite using something that includes an equality. And by default, actually, when you by default call rewrite on some hypothesis with an equality in, it will look for terms that are the same as the left-hand side of the equality, right, in the goal. So it searches for the left-hand side of equality. So we have the left-hand side of equality here, right? And it rewrites that to the right-hand side of the equality, right? So right-hand side of equality is list here. So you can if you rewrite, what has happened is you just made this a rewrite. So this term has just become this term after the rewrite, right? So after the rewrite, this just becomes the same term. So rewrite helps you do these sort of rewrites using equalities that you may have, right? And rewrite can also take an arrow. And the idea of the arrow is you're saying, okay, rewrite the left-hand side term with the right-hand side is what we are saying here. right? So it's the same as not having this term. So we are saying find the left hand side terms and replace that with the right hand side term. You can also rewrite it the other way around, right? So you can say this, and the meaning of this is rewrite wherever you find the right hand side term with the left hand side term. So what this is going to do is to check for LST and then rewrite it, right? So it's rewritten both of the LSTs here, right? So there is a LST here, there is an LST here. So it rewrites both of them. I mean, the point is, this is not leading us to the proof, right? So you can do this rewrite, you can keep doing this rewrite, but it's not going to help us prove things. So the rewrite that you actually want is to eliminate this append, right? So that we are no longer reasoning about the append. So that is what rewriting the left hand side term with the right hand side does for you, right? Once you do that, you have the same term on both sides. So trivial makes it go through because equality is reflexive. Okay, so that's how we do this proof. So there are two new tactics here, right? One is induction and another is rewrite. And what induction brings you is this induction hypothesis, which we used for rewriting the term at the appropriate place. Questions on this one? How we apply induction?
The induction tactic basically looks at the constructor of the type to fill out the
Yeah.
cases, is it? How does
Yeah.
it know to fill in those two, base case and the other one?
Yeah. So good question. Actually, it's a really nice question because when you have inductor types, there is what is known as an induction principle. So whenever you define an inductive type in Coq, right? So it defines a few things. Let's just do some simple inductive type. Inductive, say T, just as a single constructor. Okay. When I define this, it defines T, but also defines four other things, right? Actually, these three are not important, but T induction is important, right? That is basically the induction hypothesis that is derived from the shape of the data type, right? So we can sort of check what the induction hypothesis for the list type is. Okay, so if you sort of look at list induction, so this is automatically derived by Coq based on the type. When the type list was defined, it automatically sort of gives you this list induction. So what does it say? Actually, let's look at the type, right? List induction is a thing, right, which is going to be which you will use in this proof. Actually, to show you that we are using list induction, we can print the proof. We can print the proof of Append. The proof structure itself is sort of the term that is the proof of this theorem is a little bit big. We are not going to dig into the detail, but observe that we are using list induction here, right? So what is list induction? So we can check the types. List induction is what is known as the induction principle for a inductive data type. Here it is for a list. And essentially what it says is what we capture informally here, right? That in order to prove a property on a list, you want to show the base case and the inductive case, assuming the induction hypothesis, right? That is precisely what is being captured here, right? It says that for all type A, assuming there is a property P, right, that you want to prove on the list A, right? What it says is, first you need to show me that that property holds on the empty list, which is the base case, right? And next, what it says is, assume that there is an L and A and an L, right, which is the head and tail. Assume the induction hypothesis. So assuming the property holds on the tail, show me that the property holds on the const list where you append the head to a tail. So this is precisely this case, the inductive case here, right? And if you give me both of those cases, For any list at all, I can show you that the property P, whatever property that is, that property P holds on that list, right? This list induction is precisely what we are using in the proof, but that is sort of hidden thanks to the use of tactics. We are not applying it directly. But if you want to sort of dig in, maybe we can just see the base case. So list induction expects the proof for the base case, right? For the base case, the idea is that this is the property that we want to prove, right? And for the base case, all we did is we did simple and trivial, right? And if you look at the proof for the base case here, that's just equality is reflexive, right? So this is simple equality is reflexive sort of internally encodes that you need to simplify both of the terms. The inductive case I'm not going to go through in detail, but you can do that on your own time. But essentially, given that we are describing an inductive type, Koch derives the induction principle for us just by looking at the structure. It's not doing something magical. It's just like step by step doing something and giving us this very useful induction principle on the list, which is what we are using in this proof. Does that answer your question, Shashan?
Um, it does in an intuitive way, but I'm just trying to. So whatever we see in the message window there, right? When you look at the definition
Yeah.
for list inductor, I'm just trying to kind of get better at understanding that. I'm not sure if
Yeah.
I need to
So
know that, but I'm
yeah,
just
yeah.
trying to
You
kind of
don't
read
need
that.
to dig in, but it's useful to understand, right? So what are we trying to do? We are trying to prove some property on an arbitrary list, right? And the type is A, and the property can be any property at all, right? It just takes a list of A and then shows that property holds. If you want to use induction to prove that the property holds, what it says is these are preconditions, right? These are like left hand side of implication. And the way you should read it is these are the conditions that you must satisfy in order to show that this property holds, right? For all L, P of L holds. The other way you can look at it in Curry-Howard view is give me the evidence that these two property holds, right? And what are the two properties? Give me the evidence that P holds on empty list, right? That's the first base case. And second one is the induction case, right? Assuming that the property holds on the tail, give me a proof that the property holds on the const list, right? This is the base case. This is the inductive case. So if you want to use proof by induction, it says that give me the base case, give me the inductive case. I will then give you that P of L holds, right? And that is what the intuitive definition is, right? Of course, you can dig in and apply Curry-Howard thing up to uh, up to all the way down. But I think intuitive understanding is what you should aim for here. We are not going to look at this list induction in any detail. We will sort of use tactics and deal with that. Does that make sense?
Fair, fair. So just while you were talking, I ran the same thing for the day inductive type that we built the other day, and
Mm.
I think there you don't even have these constraints, right? It just directly says yes, it's provable, and here's the proof.
Yeah, because
Because
the problem,
here's what
the
you
the idea is that the
so in the
day
chat
is
window I
not
just
a.
pasted it out there. Yeah, yeah,
Yeah.
I got
So
you.
the thing is, day does not. It's an inductive type. It just has all of them are sort of. It's not a recursive thing, right? So everything is a day. A day doesn't include another day within it, unlike a list. A list is constructed by including a cons as well, right? Yeah, you can do pre-induction as well. So we can do arbitrary things, right? Inductive tree. A type is a type. Then do empty, which is a tree of A, right? And then do node, which is A to tree of A. That's the left tree of A, tree of A. right? So we defined the tree. So if you look at this, we get tree induction as well. So what do you need to show for applying induction on trees? We can check tree int, right? So it says that if you want to apply induction principle to prove some property P on an arbitrary T, right? It says that show me that P holds on the empty case, right? Show me that P holds on an empty tree. And here, I mean, it's written in an odd way, but you can move this for all here because it's on the right hand, for all is on the right hand side. So you can move it out. So it says that assume there is an A, assume there is a left hand tree T, assume there is a right hand tree T0. Show me that, assume that these are the induction hypothesis. Assume that P of T holds, P of T0 holds, and as under those assumptions, if you can show that P of node of A T0 holds, that will prove the inductive case, right? And given the base case and inductive case, you can actually show that the property holds on arbitrarities, right? So this is true for any arbitrary data type. You can construct anything, and it'll sort of give you this induction principle by default, and which is what we are using. And by the same argument, you can apply induction on any inductive data type to prove properties on it. Does that answer your question, Deepali? Okay. Any other questions on this? How induction works and so on?
I think a few exercises on this would be very nice. It seems quite
Yeah.
interesting.
So there are a lot of exercises in the second assignment. So you should certainly. I mean, I'll go through a few examples in the rest of the lecture as well. But I believe that it has some properties to prove on trees. Yeah, so I think once you get the hang of it, this will be natural, right? It's just so in this course, right? We are always learning two things. We are learning some principles, right? Ideas. Induction may not be new to you, but we'll learn ideas, but we'll also learn uh, ways of applying the idea so that in Coq, right? In Coq or F star, and if you sort of separate it out, right? When you are stumped, you sort of have to think: am I stumped because I don't understand the idea, or am I stumped because I don't know how to express this idea to Coq or F star, right? So, so yeah, so doing a lot of exercises will make you clear, and at least you can at that point ask the question and get an answer for where you are getting stuck. But anyway, so we'll continue with the more examples. The more examples we see, the better we can actually appreciate what is going on. So we are doing, we are proving that append is associative here, right? So L1 plus L2 plus L3 is the same as L1 plus L2 plus L3, right? And the way we can prove that is by induction on L1. So because if you can consider two cases, right? L1 is base case which is empty, and L1 is non-empty, and you assume the induction hypothesis as well. So which is precisely what we are going to do. So you have a type A, L1, L2, L3. So we introduce all of those variables, so they become part of the assumption, and you apply induction on L1, right? So for the first case, we have an empty here, right? Appended to, there is an implicit bracket here, right, which is not shown. So if you look at the definition, right, always sort of go to the definition and see that what simplification will give you, right? When I'm appending, if the left hand side is empty, then you just get the right hand side back, right? And similarly, the same here. When the left hand side is empty, you just get the right hand side back. So when you simplify, you just get L2 append to L3, L2 append to L3, trivially goes through, right? For the inductive case, you do the simplification, which simplifies this term first, right? And also this term. So this term is also simplified. So you have A cons L1 append to L2. this is simplified to A cons to L1 plus L2, right? So that simplification happens. And then you can see that we have the term, right? So we have the induction hypothesis, which says that L1 plus L2 plus L3, again, there's an implicit bracket here, which is not shown, equal to L1 plus L2 plus L3. And you do the rewrite, and these two terms are the same now, and trivially makes it go through. Let's see whether doing the rewrite on the other side will make it go through. So what we are doing is replacing this term with this term. When you do that, yes, so we can do it on both sides now. In this specific case, and trivial makes it go through. So we proved that append is in fact associative. Okay, so this is probably straightforward, following from just using, I mean, it's the same sort of principles as what we had seen earlier. Any questions on this? Okay, so that is on lists, right? The thing with Coq is you can prove arbitrary things about basic mathematical structures as well. So things like numbers and real numbers and fields and all of the interesting things that you have at primitive level in the language, because these are useful as well, right? So when you're writing real programs, in OCaml, if you're writing programs, you have this odd 31-bit integer or 63-bit integer. And if you're saying something about some cryptographic algorithms, you want to care about edge cases, right? Overflows and so on. So really, you have to model these low-level primitives faithfully as possible, right? Coq has a lot of libraries for dealing with 63-bit integers and IEEE floating point numbers and so on, so that you can prove certain properties there. But the simplest sort of primitive data type that we know of is the natural number. So let's prove some theorem on natural numbers. The one thing, the key takeaway from this part of the lecture is that Coq is really good at this sort of proof assistant style deductive reasoning, right? Is really good at complicated proofs. But for simple proofs, you'll be stumped, right? So you'll be like, this is so simple. I can obviously see that this is true. This is true because I studied in my second standard algebra class or third standard algebra class that 1 plus 2 is 2 plus 1. But Coq doesn't know that. You have to explicitly tell Coq that addition is commutative, right? Because you have to handhold Coq all the time. You have to tell Coq that addition is commutative, hence the thing is correct. Look at this part of the lecture as how painful simple things can be in Coq, right? But this is not to say that Coq is not good at doing things. It's just tedious for doing simple things. You will see the same level of tedium even for complicated things, right? That's the takeaway here. And the plug for F star here is F star is not just a deductive engine. So you can do this sort of inductive reasoning in F star as well. But it also has an SMT solver sitting underneath, which knows about commutativity of numbers and associativity of additions and so on, right? So if you have a complicated math formula, you just say F star, okay, I know this is true, go try it. It is very often that F star will say, okay, this is correct, right? So this is sort of this is the reason why I'm covering both of these sort of reasoning techniques in this course. Look at this example, this section of the example as what can be painful with Coq. But don't take this as everything is painful in Coq, right? It's about the same amount of pain as doing this for even complicated things, where other sort of systems, SMT solvers, sort of fall flat on their faces. That said, let's look at what we are going to do. We are going to prove the sum of sequence property, right? So it says that if you add from 0 to n for any natural number n, that's the same as n times n plus 1 divided by 2. right? So this is so we know for a fact that this is true. So let's actually do this proof in Cork. And how does the property work in for natural numbers? So if you want to prove a property on n, you first, by induction on n, you first show that for the base case, right? And then consider the inductive case, which is k plus 1, where n is k plus 1. Assuming p of k holds, show p of k plus 1 holds, right? So that is the induction principle for natural numbers, right? This is what we do typically. And in Cork, right, one of the nice things in Cork is natural numbers are also encoded as inductive data types. These are very similar to what we have seen in 3100. In GADTs, we encoded in GADTs, but also in church numerals, right? We had some 0, and then we had these additional constructors, SS, that count the number of, that actually are representative of the numbers, right? So we have a similar encoding for natural numbers in Cork. So natural number data definition is this. So a natural number is either 0 or it's the successor of a natural number, right? And 0 is O, 1 is S of O, 2 is S of S of O, 3 is S of S of S of O, and so on. Cork is just cognizant of the fact that whenever you write this natural number, it just means that SFO. And similarly, whenever you write SFO, it is the same as writing 1, just a syntactic notation that Cork has, right? And if you print the natural number type definition, you will just see that definition, right? So natural numbers is an inductive. It's a set, right? It's a data. So it's not a thing that you can prove things about. So it's a set. There are two constructors. O, the capital O stands for 0. 0 is a natural number. And for any natural number, the successor of that is also a natural number, right? That's the interpretation here. And we can even use the constructors directly for doing computations. So I'm just writing compute S of S of O, right? That's just a data value. And when you compute it, Cork actually prints that as 2, right? Cork pretty printer sort of parser and printer does not distinguish between these two notations. So that's why you see 2 here, right? And yeah, whenever we write functions, right, operations on natural numbers, they're all defined as functions internally. So these functions should remind you of, we are not going to look at any of these functions, but these functions are encoded the same way as how we encoded addition and multiplication and other operations in lambda calculus encoding lectures, right? We implemented certain operations and we said that, okay, these are going to implement these primitive operations. That is precisely how Cork is actually implementing these operations internally. You might ask, right, okay, this sounds silly. So I really want to use the machine ability for additions and multiplications. Why am I going to go through these functions? The point of Cork is proving programs, right? And towards the end of this lecture, we will see that even though the encoding of additions and multiplications and subtractions may be inefficient, you can extract efficient programs from Cork, right? Where you actually map them to efficient arithmetic, right? So we will see that. We'll come back to that. But here is the implementation of addition, right? So if you want to add a plus b, right? A plus b is going to give you a natural number. If a is 0, then it is b. If a is a successor of c, then the result is the successor of adding c and b, right? Add c and b, and that is going to give you a result. And the result of adding a plus b is just the successor of that. If you sort of stare at this definition, right, this definition is isomorphic to the append definition. So you have a list of elements, you have another list of elements, you are just putting them together to compute a list which is composed of all of the elements. We are doing the same here, right? You have a list of SS, you have a list of SS, we are just putting them together so that the same number of SS are there. And the idea is exactly the same. It's isomorphic to how we write append here. This is just a cute observation, nothing fundamental about this. But this is how additions and subtractions and multiplications are defined. Okay, so that's the takeaway here. So let's get back to proving our theorem, right? Which is sum of the sequence is n times n plus 1 divided by 2. So first, so the point of this part of the lecture is we are going to fail so many times, and then we are going to see what is the failure, what is the reason, and then we are going to come back and fix that and proceed. So firstly, you cannot even write this function naturally in Coq, right? So I'm going to define this fixed point, a recursive function for sum2, right? Which takes a natural number and then returns the sum up to that, right? So if n is 0, then it is 0, else n plus sum to n minus 1, right? This is just a sum to by adding up to n, right? This is what we would write in OCaml, right? But I'm prefixing this with fail because this is going to fail. This definition of this function is going to fail. And it says that indeed, this command has indeed failed with the message. Term n equals 0 has a type prop, and it's not a cointegral, but let's ignore that. What it's exactly essentially saying is we are using equality here, right? When you write equals in Coq, this corresponds to the equality proposition. So it returns a proposition. What we really need here is a Boolean value, because if then else operates on Boolean values, right? So this is because we've sort of stolen equality for propositions. So we need a different sort of equality that actually returns a bool. What we need is an equality which takes one natural number, the second natural number, and actually returns a Boolean when those natural numbers are the same. Otherwise, it returns false, right? And this is defined within the arith library, right? So the notation is equal to question mark. I mean, don't ask me why it is equal to question mark. It's just what it is. And if you sort of look at the definition, this has the definition that we want, right? So it has one natural number, another natural number. If those natural numbers are the same, then it returns true. Otherwise, it returns false. So that's the definition that we are going to use. So all we've done between this example here and the example here is I've replaced this equality with the equality question mark, right? And as the prefix fail suggests, this is going to fail as well, right? So when I try to implement, pass this to Coq, Coq is coming back and saying, oh, this command has indeed failed, right? And it says that, the failure condition is really interesting. Forget all of this. The important line is this one. So Coq is saying that this term n minus 1, right, is actually, so this term is not a smaller term, right? So the recursive call to sum2 has a principal argument equal to n minus 1 instead of a subterm of n. So the way to read this is, in the recursive invocation of sum2 here, I expected a smaller subterm, right? And you are giving me an n minus 1, which is not smaller. This might just seem like very crazy at the start, right? So the reason why this is coming up first is Coq needs to prove that every function, every fixed point terminates, right? So that's the thing that Coq is going to want to somehow show. So it can only accept terminating functions, right? It cannot accept non-terminating functions because non-termination is bad, right? So that's the reason why the complaint is there. But we know that n minus 1 is smaller than n, right? If I give you 5, n minus 1 is 4. Then why is Coq complaining? So first, let's look at what happens if non-termination is accepted by Coq. Okay. So here is a recursive function, right? A different recursive function. This is a digression. So we are writing an infinite loop essentially. So this infinite loop takes a natural number and then recursively calls the same function with the same argument. You can write this in OCaml, right? In OCaml, you can write this function. It will be happily accepted. Coq doesn't accept it for the same reason. It says that the argument for the recursive call, right, is x instead of a subterm of x. And essentially what it's saying is I want to show that this recursion terminates. This recursive call terminates. I can't show that here, right? What what uh, what goes wrong if we do accept this function, right? If you wrote the same function in OCaml, right, you would write it as letrec infx equals infx, right? This function will be accepted, and the type that you will get is a alpha to beta, right? So because OCaml is not able to actually show that this terminates, the type you will get is some alpha to some beta. And if you apply Curry-Howard correspondence sat and then interpret this in Coq world, the type alpha to beta would be the same as A to B in Coq. That's a proposition, right? And this function is the evidence for this proposition, which means that given an evidence for any proposition A, you can use this function to convert that into a proof for evidence for any proposition B. In particular, you can substitute true for A and false for B, and what you get is an evidence, an actual evidence for true to false. You can just apply this constructor I, right, which we know is the true evidence for true to this function if it were to exist, and get the evidence for false. Once you get the evidence for false, whole system breaks down, right? False implies anything at all. The Coq proof assistant will not be useful. So that is the reason why Coq does not accept non-terminating programs. So you might ask, right? Okay, this program is certainly bad. I want to rule it out. Why do I rule out this program? In general, this is a I mean undesirable problem, right? This is halting problem. We can't write a program that precisely determines whether another program will terminate. So this is the halting problem. We know this is undesirable, so we can't do this. So Coq goes for a imprecise solution. So we can't Coq cannot solve the halting problem. So it goes for an imprecise solution where it says that the recursive calls, right? Whenever you see this recursive function, any recursive call to that same function should be syntactically smaller term, right? It has to be able to look at the syntax and then say, okay, that term is smaller. What is syntactically smaller? The expression has to be smaller, right? In particular, when I have a term n plus 1, the expression n is smaller because it has actually dropped a few terms here, right? This is, if you think about the AST, this has a plus node and then n and 1, and you are recursing. If the recursive call is on n, then you are recursing on the subtree, right? But syntactically, n minus 1 is larger because it's a bigger term, syntactic term than n, right? So this is one rule. The other rule is when you are doing recursion, you can always recurse on the given a data type, right? If I'm recursing on a list, I can recurse on the sublist because I know that every inductive type is decreasing. So that is why we were able to call this function append here. Where is this append function? Yeah, this function, right? So we were able to call this recursive function, and Coq was able to prove that the recursion terminates because given the term ht, right, which was the argument for list 1, we are recursing on a smaller term here. So t becomes smaller, right? And Coq is able to see that it cannot infinitely go because we have inductive types which has a base case. So that is the reason why Cock was able to prove that this this recursion terminates. And it is not able to prove that in our sum2 function because we have a syntactically larger term here. So when we write n-1 here, Cock is not interpreting these as natural numbers. It's just looking at the syntax and says, okay, I'm looking at the syntax that's syntactically larger, so I'm going to reject that function, right? So that is the reason. I mean, Cock is not being intelligent here, right? It is ruling out possibly well-formed terminating functions as ill-formed, and that is the price that we have to pay. It does not mean that we cannot express this program, right? So the way you express this program is this way, right? So this is the definition that we had, which fails, right? Because n-1 is syntactically larger than n. You can rewrite sum2 by using the constructors for the natural number, right? So if n is 0, then the result is 0. If n is some k plus 1, right, I'm actually deconstructing this constructor, then the sum2 function is n plus sum2 of k, right? Because k is syntactically smaller than n, right? So this recursion, this function is the same as this one, but except that Cock can see here that k is smaller than s of k, and hence this goes through, right? So you have to play these games to convince Cock that the functions are terminating. I'll actually stop here. I've taken too much time. But what we've done so far is we've just been able to define sum2 function, right? Which represents the sum from 1 to n. Any questions on this? We can also catch up in the next class if you have deeper questions. Okay, so no short questions. We can start with questions in the
Hello.
next. Yeah, Deepali.
Syntactically, larger means just the lengthwise. Is it that?
Yeah, I mean the number of terms in the AST,
Characters.
right?
Okay.
Not the characters, the terms in the AST. So if you think about n-1, it has a minus node, right? And then n on one side and 1 on the other side. That is larger than just n, not the characters, right? So yeah, so it's the AST view, abstract syntax tree view of that particular term. Any other quick question? Okay, so let's catch up starting with questions in the next class. Thank you very much. Bye bye.